Yes. Was the last lab, um, was there an assignment uploaded on Blackboard now? Or was it okay that I emailed you the last lab report?
Last lab report you emailed me?
Yeah, because there was no way of submitting the lab report for last week.
Wait, so for the lab report, you don't see the lab report um, button to upload your lab report?
Yeah, that's correct. For lab 5 that we had, I emailed you because I couldn't see anything to upload. So
Oh, okay. Let me double check.
in the email, I also attached the lab report.
Yeah, I do receive a couple like lab report assignment. Let me see if I forgot to upload. XW. Center. So circular motion, lab 5. So the, so okay. They do have I do created a submit pathway for you to submit. Because there are other students that already submitted for the lab 5.
Oh, I don't see on my, like, even on like the to-do list, I checked. It doesn't, nothing's popping up.
Let me see. So when you tried to submit your lab report yesterday?
Sunday. I believe Sunday's when I emailed you. I can check it.
Let me see. You can try to submit it after. Okay, so so today's lecture is a little bit long, so we can try to finish the lecture, and then after this lecture, you can try to submit. If you still cannot, you can email me. Yeah, can you email? Yeah, you can email me, but I prefer you submit it on my Blackboard because then your grade will be it will have a record on the Blackboard.
No worries.
Yeah.
Yeah, it's just there's no link to submit it. But I did email you my lab report on Sunday.
Or you can just reply your previous email and to me and forward to me.
Just like say it again, like it's in the email. It's in the email.
Yeah, you
Too.
just reply because I have so many emails. So
Okay.
you can just forward your previous email and then say, oh, here's a attachment. You don't have to attach anything. You just tell me. You send me.
It's in there. Okay. Thank you.
Yeah, thank you. Okay, so share my screen. So we're gonna practice the simple harmonic motion. I think I recorded. I'm recording. So what we're gonna do is like just to go over some fundamental physics. So the first one is the Hooke's law, which the force on the spring equals to minus kx. So the minus means it's a restoring force, and the k is constant. So k is constant. It is defined by the spring, the material of the spring, or it's just like a physical. So once the spring is made, then the k is fixed. So we cannot change k, and x is the extension of the spring over its normal length and equilibrium. Let me show you the. Okay, so this is the simulation part. Let's say the intro. So you see the spring constant we can change. And there are two springs. The spring constant, 1 for 1, for 2. And you can see here is a ruler. We can put a ruler here and a timer. And so now gravity, we can also change. Now it's on Earth. So we know that on Earth, when it's on Earth, the little g is 9.8, right? And you can also click natural length. So that means the natural length of this spring. And if say we attach a mass to the spring, we stop. And then equilibrium position. So we put the equilibrium position. Now it's equilibrium. It's equilibrium. And if we wanna, okay, so we can do, okay, so so this is how we're gonna do for our lab. And another thing is like so we also use the fluid force, because when we put a mass on the spring, the spring will be extended. And then at this point, the equilibrium point, F equal to mg, right? This is the mass. And also F equal to kx. So these two will be equal. So if these two are equal, I think somewhere else. Then you can try to calculate the spring constant. Because if you know the mass, okay, so okay, let me write down something. I don't understand why. Okay, let's move to, okay, so basically, oh, I need to use another screen. Share screen. Here's the physics. Okay, so if I write down something. We only have 13 students, including me. F equal to mg, and also at this equilibrium position, it's all the total force is 0. So that means mg pointing down equals to the force pulling up, which is a spring force, equals to kx, right? So that's why, okay, see here, we have the known masses. So if we know the known masses, and we can measure the x, and we can calculate k. And so we can calculate k equal to what? Okay, after, can you see my screen?
Yes.
Thanks. So if after we calculate the spring constant, we can calculate other masses of this in this lab, right? Because we know this, we know x. X is by, you can measure with a ruler, and you can measure. Okay, so this is basically the field part of the experiment they want you to do to finish this. And so besides that, they also bring another concept of calculating a spring constant. So this way is one way. And another way is we use so the angular speed omega equal to theta over t. So now they do a derivative by using theta. So let's say what they do here is draw. So what they do here is like a circle, and here is theta. So omega equal to theta over t. So this is omega. But what if the object is circling around the circle, did a full run for the whole circle? That means the theta equal to 2 pi, right? And if it does a full circle, that means the t is periodic time t. So that's why they from this equation they derived from they have another equation for 2 pi over t. And since t equal to 1 over frequency, so that means t equal to 1 over f. So 1 over t equal to f. So that's why we have this equation here. And the acceleration a equal to minus omega squared times x. X still is the this extension of the spring. So if you put everything together, you will have a new equation of this. So then you can calculate the k by k over, because you cancel x. If you cancel x, and then k equal to m omega squared, right? And this. Okay. So you have two ways. Now you have two ways to calculate the k. The first one is the mg. Another one is by the derivatives here. And then another thing you want to know is to calculate potential energy of a spring. So if you want to calculate the potential energy of a spring, it's half kx squared, and the kinetic energy we learned previously is half mv squared. So you have these two, and later when we do the lab session here, then you will know how which equation you're gonna use. Okay, so the first one they want you determine the periodic time. So what you're gonna do is you put a ruler here, okay, from 0, and then you pull for maybe 20 centimeters, and then release. See, it's an oscillation. It starts oscillating, and you have a time for 10 oscillations, and divided by 10. Then you will have periodic time. So okay, let's see if it's on the top. We start to measure. Okay. 1. Oh, sorry. Once it reaches to the top, then we start to count. Okay. Now we start count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is 10, right? 10 is 13.9. So it divided by 10 is 1.3 seconds for the periodic time you record here. And see, you already have you have this t, and you can measure the distance here. So you can have two ways to calculate the spring constant. So you use two ways to calculate these two the same spring constant, and you compare if they have a difference between these two calculated one and why there's a difference, because I mean the errors always exist. Maybe you have the errors when you read from the ruler, or you have the errors from reading from the timer, right? So determine the percent of difference. Basically, you have K1 minus K2 divided by K1 times 100%. So you have the percentage of difference. And you determine since you already have the K, right? You have two Ks. You just pick one of them, or you take average of them, and you calculate the mass of these unknown masses. So you can finish the first part. Any questions? No? Then, okay, go to vectors. So right now we still, so you see here we can click these boxes to show, they can show us where the object is moving. And I want to have the ruler. Still it's on Earth, and you can also check these two boxes. They shows the velocity and the acceleration. Because in this point, in this section, they will ask you where is the velocity maximum and minimum, where the acceleration is minimum or maximum. So you can use this to check, but also you can use your physical background to do the see here, stop, to do the math, to do the force analysis. So basically, let's try to see, try to analyze its moment. So when we hold, so you see, then this is the equilibrium position. Equilibrium position. You see. So if I click this one, it shows equilibrium position. That means the forces are equal to each other. The force pulling down equals to the force pulling up. And after this point, so before this point, that means the spring is always increasing its speed, because it always has a net pointing down force pulling it. And after the mass crosses equilibrium position, the mass is still the same, but because the extension becomes longer of the spring, so the spring will have a longer force work on this object. So then after this point, the speed of this object starts decreasing. So that's why when, so at the equilibrium position, the speed are maximum, and at the top and bottom, the speed is 0. So, and the acceleration, you can also analyze the acceleration. When at which point the acceleration is maximum. So when their speed is 0, when it changes direction, the speed, because remember, speed is a vector. It does not only has the magnitude, it also has a vector, has directions. So when the force make the speed change its directions, that's when the acceleration is maximum. Okay, they ask you, is the gravity ever 0? Gravity ever 0? The gravity never be 0, because gravity, is mg, it's never be 0. And is spring force ever 0? Spring force can be 0 when the extension is 0. So let's say if the here, so there's no extension, right? So that's when the the spring force is 0, because there's F equal to kx and x equal to 0. It's so F equal to 0. So what happens when spring constant is increased? When spring constant is increased, that means the spring force is increased. What happens when the gravity it change to Moon, Jupiter, or planet X? So you can check, let's say this is Earth, right? We have this length, that means F equal to kx. So, and equal to mg, let me write down. F equal to Kx equal to mg. So the only thing, so because as I told you, the spring constant is a fixed value, so it won't change anywhere. You already calculate the spring constant. And let's see if we change from Earth to Moon. So this is the extension is 54 maybe. So it's 54, and the K, let's say, is 5. So we have this fixed value. So mg is fixed, and m is also physical property. So m is fixed, so you can get a little g, right? But what if we change to from Earth to Moon? You see, the extension is decreased. So like the mass is constant, the g must be decreased because otherwise the x wouldn't change. And then you can see to the Jupiter. You see, it's even longer. And what about to change to planet X? See, it's a little bit still. The little g in planet X is bigger than the little g in on the Earth, but smaller than the from the little g in Jupiter. Determine the value for gravity. Okay, then you calculate the gravity on planet X. So you basically use this equation, you can calculate the K. Because mg, you can use mg, and then, sorry, you can use kx to determine the little g, which is the gravity on planet X. See. So then, so this is for the second part. And the third part is for lab. What we do here is we still use the same, but here, let's see, I put it 100 here. You see, you can adjust the masses here, bigger, and they want you to have a 200, more than 250 grams mass, and you have 300 of the stuff. I feel so dizzy when I see that it keep moving. And we, the natural length is the natural length, and the equilibrium position, which is here. And another thing I want to notify you is damping. Okay, so here's gravity, and then damping. You see, if I have a damping here, so did you notice here the thermal? So thermal is when the energy convert to heat, and we don't know how to calculate that. So I want you to make sure close the damping, make it to 0. So when you pull, the thermal wouldn't be there, because now we basically make the whole system in an ideal environment. So there is no heat transform. So we keep the energy constant. So that's why you can calculate the energies, and you can, because there are total, for the total energy, there are total 3. One is kinetic energy, one is the gravity energy, which is a potential energy. You see the height is here, and you can make a reference standpoint. Sorry. And then you measure, use mgh to measure the potential energy. And another one is elastic energy. So for the whole system, the object does not only the spring, because in the whole system, the spring and the object has the potential energy, and the spring has the elastic energy. So as I mentioned earlier, elastic energy can be calculated by half kx squared, right? So you can calculate that. So let's see what we want you to do here. Again, you still use, you have to, okay, let me use the ruler here and the timer. So again, you want to pull for 20 centimeters. And then what you're gonna do is to time, to make it, to count for the periodic time for 10 and divide it by 10, you'll get the periodic time. And then you calculate the spring constant, because you already know F equal to mg equal to kx. You already know m and g and x. You just need for 20 centimeter. make sure you convert the centimeters to meter because they are all unified units. You make sure you use the same unit when you do the conversion. And then you can calculate spring constant. So, and then determine the energy of spring constant at the top, equilibrium, and lowest point in the oscillation. So the top energy of spring, that means a half kx. But the x here, remember when we do the measurement of x, it measures the extension. But at the top, you don't have extension, so there will be 0. And in the medium, you can calculate, okay, from 0 is like 62. So the middle point is x equal to 62 centimeter, and it's equal, the energy of the spring energy equals to half kx squared. So you 0.62 meters and square and times k and times half, that's the energy. Let me write down. So the first one, x equal to 0. The second one, x equal to 0.62 meters. And the third one, x3 equal to, because this is an equilibrium point, that means if you let it go, the let me think. If you let go, then the other half will be the same half. So you times 2. 0.62 times 2 meter. So this is how you do the you calculate the energies of the spring and determine the total energy of the system. How to determine this total energy? Stop. So you see, when the object stop moving, the kinetic energy is 0. So we want to simplify everything. Okay, so kinetic energy, we have to, if we calculate kinetic energy, we have to calculate the speed. So we don't want to bring too much variables here. So we're gonna choose somewhere with somewhere with 0 speed. So either the top or bottom. And then gravity, which is the, okay, gravity is okay, it's easy to measure. And another one is elastic energy. You calculate the extension of this spring. So what I would do is I just pick the top point because at the top point, the speed is 0 and the elastic energy is 0 too. So at the top, you see, at the top, the total energy equals to the elastic energy. Sorry, the gravitational energy. So that's how you calculate the, okay, let me write down something. For total energy H, mgh. So, the equation you use is mgh, which is E equals to mgh, and H is, remember, here is another mistake you may have. You could, like, it can confuse you because the head here is 0, and when we use a ruler to measure this part, it measures the extension of the spring. But if we wanna measure the heads, so what we're gonna do is, okay, see. So you can see. So let's say we try to calculate the potential energy on the top. which is the total energy of the system. So it's mg, h. How to calculate h? H is the distance between here and here. So you have to measure from here to here. This is the distance. Make sure you know this is the 1 meters ruler. The h equals to 97 centimeter. cm. So, okay. And another one is the one that you show the work done on the spring is equal to change in the spring potential. So at this, in order to answer this question, you have to pick 2 points. One is one is on the top, another is at the bottom. So you so what we're gonna calculate. Remember this equilibrium position. And then it's a 62, right? So that means here is 122. And what you're gonna do is measure this distance. So this is gonna be 2, position 2. And you know the h here is so you can, this is 79, it's 97. This is what? It's gonna be minus so 122 minus 97 is 25 centimeter. So the head here, the potential energy is mgh, but the h is minus 25. Just make sure, or you use minus 25. I'm gonna write. So mgh, you see here is mgh. So mg times h2 minus h1 equals to 1/2 kx1 square minus, oh sorry, I think it should be minus 2 square. Sorry, x2 square minus 1/2 kx1 square. So here h1, what is h1? h1 equal to 97, h2 equal to minus 25. See, minus 25 minus 97, this is h1 minus h2. And x2 equals to 122 centimeter. And x1 equal to 0 because it's on the top, right? So you calculate these two if they are equal to each other. And then you wanna make a plot. You wanna make a few plots based on the information you gathered here. See, since we here, since everything will be on the recording, so I'm gonna erase this. So you can, since here, you can adjust the masses. So you put the mass here, it's 100 gram, 150 gram, 200 gram, and put it here, and then the force equal to mg. And you can do the math to put the forces here. And displacement you can measure from here. You see this part is the displacement. And the spring constant, that means so F equal to mg equal to kx. So E divided by x, which is the displacement, you can have a spring constant. And these values will give you a very similar spring constant and for this spring. Then you time for the periodic time, which you do the same thing wait for 10 oscillations and use the time for 10 oscillations divided by 10. We'll have this periodic time. And then since you already have this spring constant, you can measure these two unknown masses. Use this spring constant because you don't know the mass at this point. You know kx and you know g, so you can calculate the mass here. Okay, so then you plot two graphs. One is k versus x, and you see you plot all these graphs and show me just observe the trend. Also notice in your previous lab, if you have if you think it's a linear, you try to fit all your data in the linear, but normally it's not correct. You just follow what you get, unless you have like a curved, like a very curly graph. Otherwise, your data will represent something, but don't try to fit it in a linear curve, linear relationship. And the periodic time squared, t squared versus mass. And just plot this graph, plot these two graphs from the data from this table. Then yeah, determine. Okay. Then your work is done. So another question: what effect does damping have on the screen? Like I said, the damping. If you have a damping, you see everything most of the images will transform to be the thermal imaging. That's heat. We don't want to consider heat here, so that's why we don't need damping. Okay, so any other questions? I didn't see the chat. Do you have a question in the chat?
I had a quick question about the part, I think it was the first part of the lab.
Oh.
And there were a bunch of drawings on the page that said 122 centimeters. I was wondering how you found that because the ruler isn't that long.
Oh, so
or was that just a guesstimate?
No, I was thinking, okay, so let's see here. You have this line mass equilibrium, right? Okay, let's do a force analysis. Just a second. Force. Let me draw. So let's see here. We have only mg, right? Because there's no force pointing up, right? And at the equilibrium position, that is mg. And its pulling force is Fkx. And in the end, so this Kx2 is Kx1. And mg. So so in order to go pulling this mass up, so this Kx must be like bigger than mg. And this equilibrium position, this is 62 centimeter we measured, right? So I guess I'm putting this. Oh, I want to change. Okay, so this is the mass 62. Okay, so this one is, so I would assume this mass equilibrium position is equals to the is half of its extension. You know what I mean? I mean, even maybe you don't think so because in the graph it doesn't seem like that. How to explain? Let me think. So like okay, so this is the original length of the spring. When you're pulling here, this is equilibrium position. That means your kx equal to mg. And then it will have, but it won't stop here. The mass will still go here, but with a decreased speed. It go down, down, down until the speed equals to 0. Then the speed will change its direction to pointing up, to point up. So that's why. So this one equilibrium position is a middle point. It's half of this and this. Does it make sense?
Yeah, that part makes sense. I was just confused how you got a number. If it was calculated or if it was just.
Oh, I just timed 2.
Oh, okay, that makes sense. That makes sense.
Other questions? If no other question, then we take attendance. Then, so if you still have questions you don't understand, then you can check the recordings, or you can check the recording from another class, which is from 1XB. Summer. Okay, I think I should stop recording. So we are only making a table for the last part and the 2 graphs.